96% of the total land area in Egypt consists of unforgiving desert terrain, a geographical reality that has confined 95 million people to the narrow banks of the Nile for thousands of years. Why has this ancient civilization remained trapped within such a small fraction of its territory? It would seem that the vast expanses of the Sahara offered no hope for expansion due to the lack of water. But in reality, a modern engineering feat is currently shattering these historical limits by diverting resources into the deep desert. The process of reclamation begins with the construction of a massive man-made river designed to penetrate the arid wasteland. Engineers are currently executing a project of a scale no modern nation has ever attempted before. Tens of millions of liters of water are extracted from the Nile and forced through massive pumping stations that rise like industrial monoliths from the sand. One can notice how the water surges through concrete canals so wide they mirror the appearance of natural riverbeds. The equipment gradually pushes this volume across burning deserts for distances exceeding 45 kilometers. But this is just the beginning. The water moves at a steady pace through these artificial arteries to bring life to land that has never seen a single harvest in recorded history. One can notice the heavy machinery moving in synchronized patterns to reinforce the canal walls with thick layers of concrete. The camera glides along the straight lines of the new Delta River, which was planned and operated to function in one of the harshest environments on Earth. It looks outwardly simple to move water, but in reality, the technical precision required to maintain flow across shifting sands is immense. The process is only gaining momentum as more stations come online. Because the survival of a growing population depends on this expansion, the irrigation systems are monitored by automated control centers. Therefore, every kilometer of the canal is engineered to prevent seepage and evaporation under the intense sun. Massive turbines rotate ceaselessly within the pumping complexes to overcome the elevation changes of the desert floor. It is visible how the water eventually reaches the designated agricultural zones, transforming the yellow sand into dark, fertile soil. Everything only gets more complicated as the network expands further into the interior. The new Delta River project concludes this initial phase of infrastructure, opening the road to national expansion. 110 million people inhabit a nation where the vast majority of the landscape is defined by the scorched expanse of the Sahara Desert. Why must such a massive population remain concentrated on a narrow strip of land that accounts for less than 5% of the total national territory? At first glance, the geography seems unchangeable, but the survival of the country depends on expanding beyond the banks of the Nile River. As the population count continues its relentless upward trajectory, the available arable land becomes a dangerously scarce resource, threatening the stability of food supplies. The new Delta project represents an unprecedented $10 billion investment launched by the Egyptian government in the year 2021. Engineers began the monumental task of constructing hundreds of kilometers of artificial canals and complex water infrastructure designed to bypass natural geographical barriers. This massive undertaking centers on the creation of the El Hammam pumping station, a facility of immense scale designed to move millions of cubic meters of water. A main canal stretching over 170 kilometers now cuts through the white sands of the desert, accompanied by a network of secondary distribution channels and deep underground pipelines. One can notice how the water moves through these artificial arteries at a steady, controlled pace to reach areas that have been arid for millennia. The process is only gaining momentum. Automated systems and a smart water management network utilize sensors and satellite monitoring to track every drop of liquid as it flows into reservoirs. It seems simple to merely dig a trench, but in reality, maintaining the hydraulic pressure across such distances requires precise technical calibration and constant oversight. The equipment gradually transforms the desert floor as water is distributed through the secondary channels to prepare the soil for cultivation. But this is just the beginning of the transition. Establishing long-term food security for the 21st century requires the redistribution of the population away from the overcrowded Nile Valley. The project aims to create an entirely new delta by pushing life-sustaining resources deep into the Sahara, effectively reclaiming the desert for human habitation and industrial farming. The camera glides along the massive concrete walls of the canal system, where the desert sun reflects off the surface of the rising water levels. Everything only gets more complicated as the infrastructure expands further into the wasteland, yet the goal of national stability remains the driving force behind the mechanical progress. Thus, the desert landscape undergoes a fundamental technical transformation to accommodate the needs of a growing nation. 2021 marked the official commencement of the New Delta project, signaling the start of a massive undertaking to construct a 114-kilometer artificial river. Why build such a massive structure across the arid desert? At first glance, the desert seems uninhabitable and resistant to change. But this water artery is designed to transport water from the lower reaches of the Nile River directly into the heart of the parched landscape to foster agriculture. This is just the beginning. The Egyptian government mobilized more than 12,000 workers to handle the immense scale of the project. Hundreds of heavy-duty trucks, excavators, and bulldozers operate continuously across the vast site. During the most intensive phases, long convoys of machinery line up in the middle of the desert, working 24 hours a day, 7 days a week to maintain the rigorous schedule. One can notice how the entire construction zone functions like a mobile mega-work site. Transportation routes, refueling points, and maintenance operations are coordinated with extreme precision to keep the machinery moving. The equipment gradually reshapes the constantly shifting sand dunes. It gets more complex further on. Bulldozers were deployed in massive numbers to level sand dunes and cut down high ridges. They redistribute the sand into lower areas to create a flat, stable surface. This foundation must be strong enough to support heavy construction machinery without any risk of subsidence. Survey engineers continuously check elevations and slopes to ensure uniformity along hundreds of kilometers. One can see how conveyor systems remove excess sand from the work zone while compactors compress the surface layer into a reliable foundation. After more than 2 months of stabilization, the shaping of the riverbed begins in earnest. Hundreds of excavators and trucks work together to carve a wide U-shaped cross-section into the earth. The channel bottom measures approximately 150 feet wide, with an average depth of 23 feet. This geometry allows the water to flow naturally through the force of gravity. Transition to the next level. Every single day, workers remove around 70,000 tons of sand and soil from the construction corridor. This corridor stretches nearly 250 miles toward the new agricultural plain. More than 1,200 engineers and operators labor in rotating shifts. They endure daytime temperatures that frequently exceed 115 degrees Fahrenheit under the harsh desert sun. The longitudinal slope of the entire route is controlled with extreme precision, maintaining a tolerance of just 1 inch per every 100 feet. Survey teams check elevations every 160 feet using laser leveling equipment. This ensures the riverbed remains perfectly straight throughout the entire alignment. Most of the excavated sand is reused to build embankments that form levees between 10 and 16 feet high. In elevated areas, the camera glides along as bulldozers cut the ground layer by layer. In lower zones, trucks continuously deliver reinforcement material until the design elevation is reached. Everything only gets more complicated. Specialized engineering techniques are required for sections with weak soil conditions. Engineers drill 16-inch diameter sand piles down to depths of 20 to 25 feet. In other areas, they stabilize the ground by mixing cement and clay to prevent future subsidence. Under the blazing sun and amid dust-filled winds, the long convoys of vehicles move in continuous formation. This earthworks phase lasted for many months in the western desert of Egypt. The desert sand itself poses a major challenge because it can rapidly absorb and drain away water. For this reason, the lining and waterproofing stage is considered one of the most critical phases of the New Delta project. First, the riverbed and side slopes are moistened and leveled. Then, a fine sand layer about 2 inches thick is applied to create a stable surface. Next, concrete slabs between 4 and 5 inches thick are cast in sections measuring 16 feet by 10 feet. Expansion joints are placed between each concrete segment to allow for movement. These joints are sealed with hot bitumen to prevent leakage during the large temperature swings of the desert. In areas where the ground is particularly weak, an additional high-density polyethylene waterproof membrane is installed beneath the concrete. It is anchored with steel pins and protected by a sand cover to enhance long-term durability. The process is only gaining momentum. In total, more than 124 kilometers of the artificial river were lined with concrete. This forms one of the largest waterproofing systems ever constructed in Egypt and North Africa. Along the riverbanks, engineers planted vetiver grass and other drought-resistant plants. These plants stabilize the slopes and reduce the amount of wind-blown sand entering the channel. From above, it is visible how the river appears as a bright silver ribbon cutting through a sea of golden sand. The massive earth-moving and engineering phase concludes, leaving a permanent structure in the desert. The material is ready to move to the next processing phase without haste. Thus ends one of the key stages of the new Delta project. 2 hectares. This is the approximate surface area covered by each intermediate regulating reservoir constructed once the main canal bed reaches its stabilized elevation. Why is such a massive structural volume required between the primary canal and the distribution networks? It only looks obvious to move water through a direct channel, but in reality, the uncontrolled velocity of a massive hydraulic flow would destroy downstream infrastructure without a dedicated buffer. This basin acts as a mechanical brake, absorbing and smoothing out every fluctuation in the water transition. Excavators begin forming the first reservoir zone by removing raw ground in successive measured layers. The machinery carves out a wide basin characterized by gentle side slopes, a design choice specifically calculated to ensure ground stability within the shifting sandy desert environment. One can notice how the basin floor expands to a size roughly equivalent to nearly 3 standard football fields. This is just the beginning. The process is only gaining momentum as heavy rollers arrive to compact the entire reservoir bottom into a dense, unyielding foundation. It seems simple to rely on the compacted earth alone, but in reality, the desert floor is prone to seepage and catastrophic settlement. Therefore, a specialized waterproof layer consisting of high-density polyethylene or bitumen is rolled out across the entire surface to create an impermeable barrier. On top of this protective lining, massive concrete panels are either lowered into position or cast directly in place. These panels form a durable, load-bearing shell that prevents long-term erosion from the constant movement of water. The equipment gradually moves to the edges where every single panel joint is meticulously sealed with industrial-grade compounds. It gets more complex further on. This level of precision ensures the reservoir can operate reliably for decades without structural failure or leakage. Next, technicians install the inlet and outlet control structures at opposite ends of the basin. These mechanical gates allow for the precise regulation of water levels and the measured distribution of the flow into downstream pipelines or smaller canals. One can notice how the hydraulic mechanisms are calibrated to respond to the slightest changes in volume. Everything only gets more complicated as the final reinforcement of the surrounding embankment slopes begins. The camera glides along the finished perimeter, showing how the reinforced earth transforms the open excavation into a sophisticated hydraulic buffer. The material is ready to move to the next processing phase without haste, protecting the entire downstream conveyance system from surges. 100% of the load-bearing requirements must be met before the massive concrete body of the water control weir can be established. Why is the preparation of the sandy desert soil considered the most critical phase of the entire construction? While the desert surface appears stable, its shifting nature necessitates deep foundation excavation and the meticulous shaping of the base to an exact design elevation. This ensures the structural skeleton remains immovable under the weight of the water it will eventually hold. Construction began with the arrival of heavy machinery to reach the necessary depths. Dense reinforcement steel bars were interlaced in segmented bays, creating a rigid metallic grid. One can notice how the formwork and scaffolding are then fully assembled around this skeleton, allowing for the precise shaping of thick concrete walls, horizontal beams, and massive slabs. It only looks obvious to pour concrete, but in reality, the process requires constant movement and synchronization. But this is just the beginning. The concrete is discharged continuously through the use of long-reach pump booms that extend over the site. To create a monolithic structure and minimize the presence of construction joints, the material is applied in even, controlled layers. The process is only gaining momentum as the liquid stone fills every void within the forms. Throughout the pouring phase, technicians monitor the elevation and surface flatness with millimeter precision. This is done to ensure that the future velocity of water flow does not cause localized erosion against the concrete surfaces. Once the material reaches its full design strength, the formwork is removed. revealing the completed control structure standing against the desert landscape. Everything only gets more complicated as the mechanical phase commences. One can notice the arrival of large-diameter steel pipe sections at each discharge bay. These heavy components are precisely lifted by cranes and aligned coaxially with the openings that were preformed within the concrete walls during the initial pour. The pipe flanges are pressed firmly against embedded steel base plates, then secured with high-strength bolts to guarantee watertight performance for decades. It seems simple to tighten a bolt, but the engineering team must balance the clamping force around the entire circumference. This prevents any misalignment or localized stress that could lead to structural failure under pressure. The joints are subjected to a rigorous inspection for sealing integrity, elevation accuracy, and flow direction. Transition to the next level. The regulating dam is now fully prepared for its integration with the downstream gate system and the broader water distribution network. Large steel pipe sections are installed in a sequence that extends directly from the dam structure. These form parallel conveyance lines that stretch toward the horizon. Inside the pipeline, every joint is either fully welded or flange bolted, according to strict engineering standards. One can notice the crane lowering each segment into place with slow, deliberate movements. The elevation and alignment of every section are adjusted before they are temporarily secured into position. After all connections are finalized, the entire pipeline alignment is checked for coaxial accuracy to ensure unobstructed flow. The interior is then thoroughly cleaned to remove any residual construction materials. The water distribution outlet is now ready for the final commissioning of the system. The transformation of the landscape is complete, and the infrastructure is prepared for the first flow of water. 1,500 millimeters is the minimum diameter for the specialized steel pipelines that form the next stage of the distribution network. Why was a closed branch system selected instead of traditional open-air canals for these agricultural zones? Open channels are prone to heavy evaporation in arid environments. By utilizing a network of large parallel steel conduits, the water is shielded from the sun while flowing through independent distribution branches that can reach the most remote farming sectors. The process of installation is only gaining momentum. One can notice how the ground is excavated into long, uniform trenches where the depth is maintained with millimeter precision. This allows the pipelines to be positioned at the exact design elevation required for water to move entirely by gravity, eliminating the need for constant auxiliary pumping over long distances. Some of these steel cylinders exceed 3 meters in diameter, creating massive subterranean corridors for the steady flow of the Nile. Prefabricated modules, often tens of meters in length, arrive at group staging areas in a steady logistical stream. Heavy-duty cranes then begin the slow, vertical descent of these sections into the prepared trenches. It seems simple to place pipe segments in a line, but in reality, each section must be aligned along a common axis using specialized supports and elevation instruments. This prevents operational stress and misalignment that could compromise the integrity of the line under the weight of the water. Everything only gets more complicated as the joining phase begins. The equipment gradually moves along the joints where full circumference welding is performed. Using either manual arc welding or automated systems, technicians create continuous 360-degree seals to ensure absolute water tightness. One can notice the blue flicker of the arc as it fuses the steel modules into a single, unbreakable strand. But this is just the beginning. Following the welding, each joint undergoes rigorous inspection through ultrasonic testing or pressure and leak tests to detect even the smallest microscopic gaps. Once the assembly is confirmed as sound, the interior of the pipe is cleaned of all welding slag and debris. A layer of fine sand is then placed evenly around the structure, forming a protective bedding that distributes external loads and prevents deformation from soil settlement. The trenches are finally backfilled in layers and compacted to secure the steel against the harsh desert environment. Transition to the next level occurs at the upstream end near the Nile River. One can notice the construction of an intelligent pumping station equipped with high-capacity submersible units. These pumps are directly integrated into reinforced concrete intake basins and deep intake pipes to maintain a stable flow regardless of how the river level fluctuates. Each unit is managed by variable frequency drives, also known as VFDs, which are connected to a central electrical control system. The speed of the pumps is adjusted in real time based on the actual demand of the downstream network. It only looks obvious to push water through the pipes, but in reality, a complex array of pressure, level, and flow sensors must continuously transmit data to the automated controllers. This ensures the highest level of energy efficiency while maintaining the necessary pressure across the entire expanse of the desert. After years of continuous construction, the final connection of the system is finally realized. One can notice how the water control gates are opened for the very first time, allowing the Nile to enter the newly completed infrastructure of canals and pipelines. The liquid begins to fill the regulating reservoirs, passing through control structures before advancing into the parallel branch systems located downstream. Each segment is monitored with extreme care during this initial activation to ensure the flow remains stable and safe throughout the entire network. The project transitions from a static blueprint into a functional living flow of water across the desert. Every sensor, weld, and compacted layer of earth now works in unison to transform the landscape. Thus ends the primary construction phase, and the system begins its operational life. 200,000 hectares of newly reclaimed land are emerging from the barren desert as vibrant green circles. This geometric transformation is the direct result of water arriving through a massive artificial river that has successfully reached these remote arid coordinates. Why is this specific circular formation used for cultivation across the sand? The shape is not an aesthetic choice, but a technical necessity. Huge center pivot irrigation systems are anchored to a central fixed point and rotate with mechanical precision. One can notice how these metallic arms move across the terrain like giant clock hands. The equipment gradually distributes water in an even layer across the soil, allowing the liquid to be absorbed before the intense desert heat can cause evaporation. This constant rotation turns sun-scorched sand into productive farmland that remains fertile and ready for cultivation through all 12 months of the year. The process is only gaining momentum. At first glance, the desert appears to be an impenetrable environment for agriculture, but in reality, the arrival of the artificial river redefines the entire regional landscape. These circles represent visible proof of food security expansion on a scale that was previously impossible. It does not end at this stage. Alongside the development of crop farming, massive livestock production complexes were established simultaneously on the reclaimed territory. Engineers began by leveling the empty desert plots and stabilizing the loose ground to create a foundation capable of supporting heavy industrial structures. Prefabricated steel frames were then erected in strictly coordinated phases across the subdivided land. In a remarkably short period, large-scale barns replaced the dunes, featuring reinforced concrete floors and heavy structural columns to support expansive roof systems. 6,000 head of cattle can be housed within a single integrated complex designed according to a modern industrial model. Everything only gets more complicated as the infrastructure integrates different life support systems. The open barn architecture utilizes natural ventilation and sun shading, which is essential for the herds to adapt to the arid climate. Branching off from the main conveyance network, dedicated pipelines supply water for sanitation, cooling, and hydration for the animals. One can notice how the water management system maintains a constant flow to the livestock zones. Feed for the cattle is produced directly from the surrounding circular fields, forming a closed-loop system where crop production and animal husbandry are physically linked. The process is only gaining momentum as the domestic supply chain receives beef directly from these desert facilities. This logistical integration reduces the national reliance on imports and ensures a stable flow of food to the market. The desert transformation concludes this phase, opening the road to long-term regional stability. Tens of billions of dollars is the estimated capital expenditure invested into the construction of this monumental hydraulic artery. Why did the state commit such vast financial resources to a single engineering endeavor? One might assume that a simple canal would suffice for irrigation, but the technical complexity of diverting the Nile required a decade of continuous labor. This investment serves as the physical foundation for the new Delta project, where the artificial river acts as the primary life support system for an expanding agricultural territory. The process is only gaining momentum. Engineers and laborers have spent nearly 10 years shaping the landscape to accommodate the flow of water across once arid terrain. One can notice how the concrete embankments stretch across the horizon, cutting through the sand with geometric precision. This scale of construction is merely a preliminary phase when compared to the projected long-term economic yield the infrastructure is expected to generate for the nation. At first glance, the new delta appears to be a solitary river cutting through the desert, but in reality, it represents a total transformation of the regional ecosystem. The project encompasses more than just the movement of water from its source. It integrates specialized infrastructure, modern agricultural techniques, and a comprehensive food production network within a single unified system. Everything only gets more complicated. Land that was once characterized by barren geological formations is being systematically repurposed for high-yield cultivation. From the initial irrigation of the soil to the final stages of the food supply chain, every element undergoes a complete technological reconfiguration. One can notice the mechanical systems and livestock facilities appearing where previously only sand existed. It is visible how the new landscape supports crops and sustainable farming practices that were impossible a decade ago. This shift establishes a self-sustaining cycle of production that begins with the flow of the artificial river and ends with a stabilized food supply for millions. The project concludes this phase, opening the road to a permanent transformation of the desert geography. This marks the completion of one of the most significant stages in the structural evolution of the regional environment.